This is the second video of Chapter 20 dealing with transfer variables and the first law of thermodynamics. We can describe a system in terms of state variables. State variables are a macroscopic approach to thermodynamics, and they include things such as pressure, temperature, volume, the three variables that are involved in the ideal gas law, and we can also include internal energy. These state variables describe the state of the system in a macroscopic way. On the other hand, we can have variables that are involved with the transfer of states of a system. Hence, they're not associated with any given state of the system, but its transfer. And this would involve an energy transfer in order to change the internal energy of the system. Involved with these transfer variables are heat and work. Let's take a little bit closer look at these transfer variables, work and heat. Consider a compression of a gas, say with a piston. Cross-sectional area of the piston is A, and we're going to compress it some displacement delta Y. This compression is going to be quasi-static, which means it's going to be very, very slow, allowing the system to equilibrate at every little juncture along the way as we're compressing the gas. So the work done on this gas would be equal to the negative force times the displacement delta Y, which I could write as the force as the pressure times the area as we're applying it on this gas, the area being the cross-sectional area of the piston. I'll rearrange this, and that's equal to the negative pressure of the area times the change delta Y, which I could say is equal to the negative pressure times the change in volume. And now as we're compressing this gas, the final volume will be less than the initial volume, so I can imagine that this delta V is going to be a negative quantity, and hence we're doing work on the gas as a positive value because it's going to be negative, negative. So delta V is the change in volume of the gas, and on a PV diagram, this process might look something like this, where we're graphing pressure versus volume. We start at some initial volume, and then we compress it down to a lesser final volume, and the area underneath this graph, since it's a rectangle and pressure and change in volume, the area underneath that graph would be the work on the gas. So if the gas is compressed, our change in volume will be a negative quantity. The work, which is the negative pressure times the change in volume, will be a positive quantity. So the work done on the gas will be a positive quantity. If the gas were to expand, change in volume will be a positive quantity, and the work done, quote, on the gas would be negative, because it would be a negative P times change in volume. If the volume were to remain constant, the work would be zero, because the work has to involve a change in volume. In general, the total work done on the system and this gas is equal to the negative integral from initial to final volume of the pressure integrated with the volume. This would include a possibility that the pressure was not constant. It could actually change as we're going through this process. In this case, this work would be the negative area under a P versus V graph. The work done depends on the path taken from the initial to the final states then, because it involves the area underneath this graph. If I were to go from, on this pressure versus volume PV diagram, if I were to go from initial volume to final volume and increase my volume, the gas were to increase, the gas is actually doing work on something else. So in this case, the work on the gas would be a negative quantity. If this process were to go to the left, so I'd go from a larger initial volume to a smaller final volume, then the work on the gas would be a positive quantity. Here are some other PV diagrams. Constant volume and then constant pressure. So if I were to at constant volume, decrease the pressure from some higher value to a lower value, the work in that case actually would be zero. There would be no area underneath that arrow, underneath that graph. But then if I continued at constant pressure, I would change my volume from initial to final. The work would be equal to the area of that rectangle, pressure times the change in volume. Here's another graph. It's at constant temperature, called isothermal, and again the work done on the gas would be a negative quantity of the area underneath the graph, or we can think of it as the work done by the gas would be this positive area underneath the graph itself. And here's another process where we allow an expansion from initial to final volume, but we don't allow any heat exchange when it's doing that. And under those conditions, we call the expansion adiabatic. So what generally will happen is we'll start from one internal energy, expand as the gas is doing work, but the internal energy will have to go down because the gas has expended some of its energy in doing work on the outside, and there was no possibility for replenishing that through heat exchange. So adiabatic expansion, we would have to cool our gas down to a lower internal energy and lower temperature. This takes us to the first law of thermodynamics. And it's basically a statement of the conservation of energy. We're stating that the change in internal energy of a system is due to the transfer variables. So it's equal to the heat added to the system plus the work done on the system. And we write it as the change in internal energy is equal to the heat added to the system Q plus the work done on the system W. And each of these variables, each of these transfer variables, Q and W, we're doing something on the system. So to be a positive, it's got to be done on the system, thereby affecting a change in the internal energy of the system in a positive way, if you think of it that way. So if Q is positive, W is positive, and internal energy will go up. If Q plus W is negative, then the internal energy will change and go down. And the final will be less than the initial. So we have to think about this first law in this form as what we're doing on the system. Now, you probably will see other courses where you'll see this first law in different forms, and sometimes Q will be on the system and work will be by the system, and vice versa, and it can be confusing. But in this form, as we're showing it here, everything is on the system. Change in internal energy would depend on a transfer of energy. If the system is isolated, then the change in internal energy will have to be zero, and whatever Q we have will be equal to the work will be equal to zero. So our change in internal energy will be zero. And the internal energy then will be constant, no change. Let's try out an example. 2 cubic centimeters of water are boiled at atmospheric pressure to become 3,342 cubic centimeters of steam, also at atmospheric pressure. All this is done at constant atmospheric pressure. Calculate the work done on the gas during this process. All right, so we're doing this at constant pressure, but we're going to have a change in volume of our substance. We're going to go from 2 cubic centimeters of water to 3,342 cubic centimeters of steam, and that will be our change in volume. So, since we're isobaric, the work will be equal to negative pressure times the change in volume. That's going to be a negative 1 atmosphere, which is 1.013 times 10 to the 5 pascals. And our final volume will be 3,342. Our initial volume was the volume of the liquid water, which was just 2. All this is cubic centimeters, which is going to be 10 to the minus 2 times 10 to the minus 2 times times 10 to the minus 2, which is 10 to the minus 6 cubic meters. And this gives us, in the SI system, negative 338 joules. Find the amount of heat added to the water to accomplish this process. If we're going through a phase change from liquid to gas, then that would involve the mass of the substance times the latent heat of vaporization. So our Q is going to be the mass times the latent heat of vaporization. The mass in this case is 2 cubic centimeters of water, which corresponds to 2 grams if it's pure water by definition. So that's going to be 0.002 kilograms of water times the latent heat of vaporization for water, 2.26 times 10 to the 6, gives us 4.52 times 10 to the 3 joules. So the Q added to the system to make this happen is 4.52 times 10 to the 3 joules. The work done on the system to make this happen is a negative 338 joules because the gas actually did work out of the system. It expanded and was doing work itself. So we have negative work done on the gas. Hence, our change in internal energy by the first law of thermodynamics is equal to the Q added to the system plus the work done on the system. 4,520 joules plus a negative 338 joules is 4,182 joules. And that will be our change in internal energy of this system. A cyclic process starts and ends at the same state. Hence, the change in internal energy should be 0. We're going to be right back where we started. There should be no overall change of that system. But it's not isolated. We could have an exchange of energy transfer. It's just that once we get back to our original state, the total change in energy is 0. So for a cyclic process like this, with delta E internal being 0, the Q should equal a negative W. The Q added to the system should equal a negative of the work done on the system. If we look at a PV diagram, the net work that is enclosed as we go through a cyclic process, the area enclosed as we go counterclockwise is equal to the work done on the system. We can think of that as work being done on the system every time we go from higher volume to lower volume, and hence the large rectangle is going to be a greater area than the small rectangle down below when we subtract that. So we basically are left with the area of this little rectangle that I've shown here with the arrows going counterclockwise, and that's the work done. Since the heat added to the system is the negative of the work done, the area going clockwise, the other way around, enclosed in that, is the heat added to the system. Let's try this out. A gas is taken through the cyclic process described by the figure. We're going to go from A to B, which is 2 kilopascals to 8 kilopascals and 6 cubic meters to 10 cubic meters. Then we're going to go from B to C, 8 to 2 at constant volume, change of pressure. And then at constant pressure, we're going to go from 10 cubic meters down to 6 cubic meters. So we want to find the net heat transferred to the system during one complete cycle in this sense. Let's find the work done first. It's the negative area underneath this graph, or contained within this graph as we're going through a cycle. So we want to find the area of this triangle, basically. And that's going to be a negative 1/2. Our base is, or our height is 8 minus 2, or 6, times 10 to the 3 pascals. And our base is 10 minus 6, or 4 cubic meters. This gives us a negative 1.2 times 10 to the 4 joules for the work done on the gas. The heat added to the system is a negative of the work done because it's a cyclic process. and hence the heat added will be a negative work, 1.2 times 10 to the 4 joules. So that's how much heat was added in this cyclic process. If the process went the other way around, then the heat added would be the negative of this, and the work done would have been a positive quantity on the gas. Here's a special process, the adiabatic process, which we hinted on before, means that we have an isolated system in such a way that no heat is added to the system as we go through our process. No energy enters or leaves the system by heat. This can be achieved by thermally insulating the walls of the system so well that heat can't be exchanged, or by doing the process so quickly that heat doesn't have a chance to be exchanged. And oftentimes that's the way the adiabatic process works. We do it so quickly that we don't have a chance for exchange and equilibrium to take place between the system and the environment outside. Since the heat added to the system is equal to 0, our change in energy by the first law will simply be equal to the work done on the system. So if you compress a gas adiabatically, doing positive work on the system, all that energy of the work will go into the internal energy of the system. Work will be greater than 0, and your change in internal energy will be greater than 0. The energy of your system will go up, and since the energy of your system is proportional to your temperature, the temperature will go up. So the gas temperature will go up. If we went the other way around, if the gas were to expand adiabatically with no heat exchange, then the gas is doing work to the outside. The work done on the gas would be negative, and our change in internal energy would be negative, and hence our temperature will go down. Our final temperature will be less than our initial temperature, and we will cool the gas by doing that. So adiabatic expansion will cool the gas, and adiabatic compression will heat the gas up. So in this adiabatic process, we have a transition between two states of energy, and possibilities of examples: the expansion of hot gases in an internal combustion engine, the liquefaction of gases in a cooling system, possibly a refrigeration system, or the compression stroke in a diesel engine. The diesel engine doesn't have a spark plug, so it uses the compression stroke to change the temperature to such a point that will cause combustion. So these are all examples of adiabatic processes. In the isovolumetric process, we have no change in volume, so there's no work done. You have to have a change in volume to have work done. So isovolumetric process is one that occurs at constant volume. Since the volume does not change, work is 0, and from the first law, our change in internal energy will simply be equal to the heat added to the system, also called an isochoric process. Isobaric process is one that occurs at constant pressure. The values of the heat and the work generally would not be 0. The work done is the negative pressure times the change in volume in this case, and where the pressure would be constant for an isobaric process. Isothermal process. Well, we know that one state of our system is the temperature. So that's going to determine our internal energy. So if we were to stay at the same temperature, if we were isothermal, same temperature, then our change in internal energy will have to be 0, because we're not going to change our state based on the temperature. So isothermal process is one that occurs at constant temperature with no change in temperature. Our change in internal energy will be 0, and hence by the first law, 0 will equal Q plus W, or our Q, heat added to the system, will be equal to a negative work done on the system. Any energy that leaves the system by heat must leave the system, or enters the system by heat must leave the system by work in order to maintain a constant temperature and a change of internal energy of 0. We wish to look at this isothermal process a little bit more in depth. Here's a PV diagram of an isothermal process, and as we said, everywhere along this hyperbola is a constant temperature, a constant state for the gas. For ideal gas, we know that PV equals nRT. So if T is constant, we have that the pressure times the volume is constant, and we have an inverse relationship between the pressure and the volume. A hyperbola. And this curve is what we also call an isotherm. In an isothermic expansion of a gas, the work done on the gas should be a negative integral from initial to final volume of P dV. In this case, the pressure is a function of the volume. And in fact, for an ideal gas at constant temperature, we can substitute in for the pressure as being nRT over V from PV equals nRT. So we've substituted in for the pressure, but we realize it's an isothermal expansion. So the temperature is constant. Anytime you have a constant in an integral, you can take it out of the integral. And N and R are constants as well. So we're going to take those out of the integral, and we have that the work is equal to negative N times R times T. And now we have the integral from initial to the final volume of dV over V. You know what that integral is. It's the natural logarithm of, in this case, V, evaluated from initial to final volume. So the work done on the isothermal expansion of a gas is equal to nRT, natural log of our initial volume over our final volume. Because the log would have been final volume over initial, but if you reverse those, you're going to introduce a negative sign, and hence we've canceled out the negative sign here with that. So the work is equal to nRT, natural log, initial volume divided by final volume. Since the heat added to the system is a negative of the work done, the Q added to the system is nRT, natural log of the final volume over the initial volume, because we reverse those again to introduce the negative sign. So here's a summary of our special processes with the first law and transfer variables. If we have an adiabatic process with no heat, Q is equal to 0, and in this particular case, by the first law, change in internal energy is equal to the work done on the system. Any work done on the system will go into a change of the internal energy in the state. Isovolumetric is a constant volume, which means we can't do any work. So no work done either on or by the system. And in that case, by the first law, the change in internal energy is equal to whatever heat we add to the system, positive or negative. Isobaric is done at constant pressure. In this particular case, the work is equal to negative pressure times a change in volume, final volume minus initial volume. And for that matter, we would apply the first law, because we will possibly have a change in internal energy, and that will equal the heat added plus the work done on the gas. Isothermal is at constant temperature, so we have no change in internal energy. Hence, Q will equal a negative W and will equal nRT natural log V initial over V final, like we saw on the previous screen. So here's a quick summary of some processes by the first law. We'll get into this a little bit more in the following chapters.